So, let us continue with the earlier class, where we have discussed the algorithm of the two-phase method and we have shown example. If you remember, on that example we have shown that in the phase 1, whatever solution you are obtaining there, artificial variable was not present in the basis. That means, maximum value of z star was 0 and basis artificial variables was not present there, and we obtain the optimal solution using phase 2 method. Now, let us take up another example of different type. Please see this one. Maximize z equals 3x1 plus 2x2 subject to 2x1 plus x2 less than equals 12, 3x1 plus 4x2 greater than equals 12 and x1 x2 greater than equals 0. So, I have to convert this one into standard form first by using the slack variable, surplus variable and artificial variable, since you have one less than equals type constant and another one greater than equals type constant. So, your problem is in standard form. I can write down maximize z equals, I am writing this later 3x1 plus 2x2, I will write down the others afterwards, subject to 2x1 plus x2 plus x3, this is equals to, where x3 is the slack variable. Please note this, corresponding to this less than equals inequality, and 3x1 plus 4x2 minus x4 plus x5, this equals 12. So, here your x4 is the slack variable, surplus variable, and x5 is the artificial variable. So, that here you will add accordingly 0 into these things, 0 into x3 plus 0 into x4 plus 0 into x5. Means, again I am repeating this, for artificial variable in two phase method the coefficient is 0, not like big M method where he was using the coefficient as minus m, and your x j is greater than equals 0 for j equals 1 to 5. This is your problem. If you see, for this case, initial BFS, basic feasible solution, will be x 3 equals 2. That means, by making x 1 x 2 are the original equations. If I make x 1 equals 0 and x 2 equals 0, in that case I will obtain, this implies x 3 will be equals to 2 and x 5 will be equals to, from this equation x 5 is equals to 12. So, that your x 4 automatically becomes 0. So, the initial basis two variables will come, that is x 3 and x 5, that is one slack variable and one artificial variable x 5. Now, your auxiliary objective function, which we are denoting say z star, will be equals to 0 into x 1 plus 0 into x 2 plus 0 into x 3 plus 0 into x 4 minus 1 into x 5. As we have told, with artificial variable we will the coefficient will be minus 1, whereas for all other decision and slack and surplus variables the value will be 0. So, this is the new auxiliary objective function, and I have to now optimize this auxiliary function subject to the original set of constraints. So, in this case your in the basis you have two variables, that is x 5 and x 3. It is your a 5 and a 3. Values are 0, 0, 0, 0. For x 5 only coefficient is minus 1. So, here it will be minus 1, 0. So, I am writing, I have to write down corresponding to x 5, means the second constant first. I can write the other way also. first x 3 then x 5, the problem will remain same. So, it will be 3 4 minus 1 sorry 3 4 x 3 is not there. No, your b is 2, sorry, I am sorry. Your b is here 12. So, this is your 12. So, it will be 2, then 12, after that it is 3, then it is 4, x 3 is 0, minus 1, 1. So, it is here b value is 2. So, it will be 2, 1, 1, 0, 0. If you calculate the zj minus cj value as usual, cb into xb minus cj, you will obtain minus 3, minus 4 and 0, 0, 0. This is 1. So, it will be 1 and this will be 0. So, zj minus cj is less than equals 0. Therefore, most negative is minus 4. So, entering vector will be this one. Most negative zj minus cj is minus 4. So, entering vector is this. So, now I have to calculate the ratio, that is here it is 12 by 4, that is 3, and for this case it is 2 by 1 2. So, your entering variable, departing variable will be x 3. So, your x 3 is going out and x 2 will enter into the basis, and your pivot element is this one, intersection of the corresponding row and column of the departing vector and the entering vector. So, this is already 1, I do not have to do anything to this row, I have to make this element as 1 for this element as 0 for manipulation. So, for this case your x 3 will be replaced by the x 2. So, that you will obtain x 5 and x 2. All other things will remain same, that is 0, 0, 0, 0 and minus 1. Here it is a 5 and a 2. So, that your C b will be minus 1 and 0. So, second row will remain same, that is it will remain 2, 2, 1, 1, 0, 0, and the first row I have to make 4 as 1. So, I have to make this one as 1. So, it will remain 4, minus 5, 0, minus 4, minus 1 and 1. So, it will be this, in this case it will not be 4, I think, just 1 minute. So, it will be 12 is there, 12 divided by 4. So, this value will be 3. Now, calculate the zj minus cj value. Zj minus cj value will be 5, 0, 4, 1, 0. So, if you see your zj minus cj is greater than equals 0 for all j. So, what will be the conclusion? The conclusion is that whether should I go to phase 2 for the optimal solution. This is your basic feasible solution or BFS, but this will not give you the optimal solution because of the case that your artificial variable x 5 is present in the table. Please see this one, your x 5 is present in the basis, this x 5 is present in the basis. So, according to our algorithm, if zj minus cj greater than equals 0 and basic variable is present in the basis, then there will be no solution. There will be no solution. So, this is the second type of problem. Although zj minus cj is greater than equals 0, but the basic variable is present, artificial variable is present in the basis. Therefore, the problem will have no solution. We can check it graphically also. For this case, your problem was, if you remember, your constraints was 2 x 1 plus x 2 less than equals to, and 3 x 1 plus 4 x 2 greater than equals 12. If I draw the graph of these things, I think there will be 1, 2, if I make it 2, somewhere 3, somewhere say 4, and in this case 1, 2 and 3. So, 2 x 1 plus 1 2, that means 1, and if x 1 0, x 2 is 2. So, one line will be this one, which is 2 x 1 plus x 2 equals 2. It is less than equals 2. So, this side. Other one is 3 x 1 plus 4 x 2 equals 0, that is x axis will be 4, y axis will be 3. So, the line will be something like this. This is 3 x 1 plus 4 x 2 equals 12, this line, and it is greater than equals 2. So, the direction will be on this side. So, if you see on the positive side, for the line 2 x 1 plus x 2 is less than equals 0 means this area, whereas for 3 x 1 plus 4 x 2 greater than equals 2 means this area. So, basically there is no region which is common to these two lines and the coordinate axis, or in other sense there is no feasible region, and if we know that if there is no feasible region, then there will be no solution of the problem, and which we have seen it by two phase method also. Without going to the second phase, on the first phase itself, whenever you have observed that Zj minus Cj is greater than equals 0, but the artificial variable is present in the basis. Therefore, we have concluded that there will be no solution for this problem, and this particular there is no need of going to phase 2, which we confirmed by the graphical method also, drawing the constraints on the two dimensional plane, that there is no feasible region or no area is common to both the lines as well as the positive coordinate axis. Now, let us take the other example, some other example of other type. Say it is z equals 2 x 1 plus 3 x 2 plus x 3 subject to these two equality constraints. So, here you do not have the less than equals or greater than equals constraint, but you have the equality constraints for both. So, in standard form, first I have to write down maximize z equals subject to minus 3 x 1 plus 2 x 2 plus 3 x 3. As I was telling earlier, whenever you have the equality constraint, if required, I have to use the artificial variable. And please note that if I do not use the artificial variable from the given constraints, these two equality constraints, I cannot obtain the initial solution, initial basis or basic feasible solution. Because if I make all the variables x 1, x 2, x 3 equals 0, that is not satisfying my condition. So, we are adding some artificial variable for both. So, therefore, it will be plus x 4 and for the second one minus 3 x 1 plus 4 x 2 plus 2 x 3. Here it will be 0 into x 4 plus x 5 is the artificial variable. So, for this case 0 into x 5, this is equals 8, this is equals 7, x j greater than equals 0 for all j and maximize z equals minus 3 x 1 plus 2 x 2 plus 3 x 3. So, for this case, please note this one, initial BFS is equal to x 4 is 8 and your x 5 this is equals to 7. initially you are obtaining this one. And that is the only reason we have to incorporate artificial variables for this particular problem in both the equality constants. So, sometimes if required in the equality constants, we have to add the artificial variable depending upon the requirement of the problem. So, now what I have to do? I have to create the auxiliary objective function, and I will try to go for the simplex method for the auxiliary objective function subject to the original set of constraints of the standard equation whatever we have written now. So, what is the auxiliary equation? Auxiliary equation in this case z star will become your variables, decision variables are x 1, x 2, x 3. So, therefore, 0 coefficient will be assigned, whereas for the other two cases it will be minus 1 into x 4 minus 1 into x 5, because x 4 and x 5 are the artificial variables. So, now in the phase 1, let us go for the simplex method. Your x b is x 4 and x 5. So, it is a 4 and a 5. Here it is 0, 0, 0, minus 1 and minus 1. Your C b is minus 1, minus 1. Your b value for both is 8 and 7. So, let me write down this equation, coefficients of the respective variables from the constants. So, minus 3, 2, 3, minus 3, 2, 3, then it is 1, it is 0. For the next one, it is minus 3, 4, 2, 0 and it is 1. Value of z j, if I calculate using the formula, you will obtain 6 minus 6, 5, 0, 0. So, therefore, you have a negative, most negative is minus 6. So, corresponding to this column variable is x 2. So, your entering vector is x 2 for this case, and I have to calculate the ratio. Now, the ratio for this case 8 by 2 4, for this case it is 7 by 4. So, 7 by 4 is minimum. So, your departing variable for this case will be x 5. So, therefore, in the next simplex table of phase 1, x 5 will be replaced by the variable x 2. So, you will obtain the table like this. X 4 will be as it is, you will have x 2. So, here you are writing a 4 and a 2, here it is 0, 0, 0, minus 1 and minus 1, x 4 coefficient is minus 1, for x 2 it is 0. Sorry, in this case your pivot element was 4, that means I have to make this element as 1 and all other elements of this column as 0 by manipulation of the rows. So, if I write down directly, I will obtain 9 by 2 minus 3 by 2, 0, 2, 1 minus half. For this case, you will obtain 7 by 4 minus 3 by 4, 1 half, 0 and 1 by 4. From here, if you calculate the z j minus c j value, z j minus c j value will be 3 by 2, 0, minus 2, 0 and 3 by 2. So, for this case, it is becoming again z j minus c j value is not greater than equals 0, one negative is still there. So, I have to continue the iteration. So, in this case your entering variable will be x 3. So, corresponding to this I have to calculate the ratio, it will be 9 by 4 b by x b, whereas for the second one it will be 7 by 2, 9 by 4, 7 by 2. So, minimum is this one. So, in the second iteration your departing variable is x 4 and your entering variable will be x 3. That means, x 3 will be replaced by x 4. So, here it will come x 3 x 2, a 3 a 2, values are c j's are remaining same. So, CB will be 0 and 0 in this case. So, here again if you see your pivot element is this one, your pivot element is half. So, therefore, I have to make this element as 1 and other elements as 0. So, I am writing this row at first. So, this row will become, I am sorry, not this row, not this one, I am sorry. Intersection is this point, this column and this row. So, pivot element is 2, not this one. So, I have to make this element as 1 and all other elements as 0. So, that you will divide by 2, you will obtain in this case 9 by 4 minus 3 by 4, 0, 1, half minus 1 by 4. To make it 0, you will have 5 by 8 minus 3 by 8, 1, 0, minus 1 by 4 and your 3 by 8. So, by making this one as 0, we are making this one, this as 1 and this element as 0, we are performing the row operations on these two. Now, calculate the Zj minus Cj value. Zj minus Cj value for this case 0, for this case 0, for this case it is 0, for this case it is 1 and for this case it is 1. So, now your Zj minus Cj is greater than equals 0 for all j, that is x1, x2, x3 and x4. Now, in this case what is happening? All Zj minus Cj greater than equals 0 and no artificial variable is present in the basis. So, there will be basic feasible solution and we have to go for the phase 2 with the original objective function, that is original coefficients of the decision variables and other variables. So, let us go to the phase 2 of this. Now, on the phase 2, if you see this table will remain as it is. Please note this one, the last table, that is this table, all the values will remain as it is. The only change will come on the Cj's, that is this coefficients now will be the proper one. And also note another thing, we had two artificial variables in our problem, x4 and x5, and the variables, artificial variables x4 and x5 are not present in the basis. Therefore, we will remove also these two columns, since artificial variable is not present over here. So, whenever we are going for this, we are having x3 and x2 and here it is a3 and a2, whereas the Cj values will be of your original problem was 2, 3 and 1. So, it is 2, 3 and 1 will come as a coefficient for the variables x1, x2 and x3. So, we are writing here 2, 3 and 1. So, you are obtaining this as 1 and this as 3. So, correspondingly the values will remain same, that is 9 by 4 minus 3 by 4, 0 and 1, and the values for x4 and x5, if you see we have removed the values for x4, sorry, the columns for the artificial variables x4 and x5 from here, since the artificial variables x4 and x5 are not present in the basis. So, the next one is 5 by 8 minus 3 by 8, next one is 1 and it is 0. If I calculate the Zj minus Cj value now, Zj minus Cj value will be 1, that is minus 3 by 4 minus 9 by 8 minus 2. So, it will become minus 13 by 8. This one will be 0, 3 minus 3, it is 0. For this case 1, this is 0. So, 1 minus 1, 0. So, here if you see your Zj minus Cj is not greater than equals 0, that is one value which is negative. So, in this case your x1 will be the entering vector, your x1 will be the entering vector. Therefore, I have to calculate the ratio. Whenever you are trying to calculate the ratio b by xb, that is this value is minus of this 9 by 4 divided by 3 by 4, and for this one it is minus of 5 by 8 divided by 3 by 8. Please note this one. In this case, both the ratio values are negative, but if you remember, we have this condition always earlier, that is this value should be greater than equals 0. This should be 0 or positive, this cannot take negative values, and whenever this takes the ratio takes negative values, both are negative here, and if the both are negative, that means I cannot take the negative values here. Since I cannot take the negative values, that means I cannot enter or I cannot depart any variable here. So, please see the situation where I have an entering vector, but what will be the departing vector, that is not clear. That is x3 can be departed or x2 also can be departed. Therefore, in this type of cases, whenever your ratio is negative or infinity, in that case, if both all the ratios are negative or infinity, you will have unbounded solution. That means, no optimal solution, always we will be obtaining the unbounded solution. So, this is another case where if the ratio is less than equals 0 negative, then the solution will not be present there and you will obtain the unbounded solution. So, you see, you can obtain the unique solution, you can obtain infinite number of solution, you may obtain no solution, and that from two phase method without calculation after phase 1 you can tell, or the last example which we have explained, that is the unbounded solution. This unbounded solution also we have discussed graphically. Now, for two phase method also we have shown this one. So, I hope it is clear the two phase method. In the next lectures, we will discuss some special cases of linear programming problem.